Well, now we are moving into chapter 13. And with that, we are looking at the properties of solutions. We were looking at the properties of solids and liquids, and now we're looking at properties of solutions when things are a mixture in a liquid. So a solution is, the definition of a solution is a homogeneous mixture of two or more pure substances. And you can have a variety of different mixtures, and it's dependent on what are the states of the solvent and the solute. And you can kind of look at this example here. So like air is an example of a mixture of gases where one gas is the solvent and another gas would be the solute. But in a solution, you always have a solute and you have a solvent. The solute is the thing that is dispersed uniformly through the solvent, meaning you're always going to have more of the solvent than the solute. Okay, you have to have, the solvent has to be the thing that you have more of that the solute then dissolves into. So in solutions, the intermolecular forces between solute and solvent particles must be strong enough to compete with those between the solute particles themselves staying together. So if you had, when you try, let's say you take a gold ring and you want to try to make a solution of gold in water. Well, water, although is a very polar molecule, it does not dissolve the metal of the gold metal on the ring because the intermolecular forces of water, the hydrogen bonding, is not strong enough to break up the metallic bonds that exist between the gold atoms in a gold ring. So how does a solution form? For a solution to form, the solvent pulls the solute particles apart and surrounds or solvates them. So here we have an example of sodium chloride, a crystal of sodium chloride. And as the water molecules come in contact with the outer edge of the sodium chloride crystal, the polar ends of the water molecule are attracted to the polar ions of the sodium chloride, or the sodium or the chloride separately. So you notice in this center image, the purples are surrounded by the red end of the water molecules, and then the greens are attracted by the white ends. Now, if you think of a water molecule, the red ends are going to be the negative ends of the water molecule because that's the oxygen end, which is the negative end, the more electronegative end of the water molecule, and then the whites represent the hydrogens, which would be the more positive. So the whites are attracted to the chlorine atoms, which are negative, or ions, and the red ends of the water molecules are attracted to the sodium ions, which are positive. So they pull apart in that process. So how does a solution form? If an ionic salt is soluble in water, it is because the ion-dipole interactions are strong enough to overcome the lattice energy of the salt crystal, meaning pulling it apart, making it, the lattice energy is not as strong as the water ion attraction that would be present. So energy changes in solution. So when you have a solid and it goes into the gas phase, or you have a solid that turns into a liquid, you have certain energy associated with it. But there's three processes that affect the energetics of solutions. First, there's the separation of solute particles. So that's that first one. So if you have the solid and then all the little particles separated, there's some energy associated with that. Same thing goes for the separation of solvent particles, because when you have solute kind of interacting with the solvent, you're separating or kind of changing the intermolecular forces in the solvent as well. And then when you combine those two together, you have new interactions between the solute and the solvent. So all of those are delta H's for that type of reaction. So when you think of a solvent and a solute combining to make a solution, you can put all of those delta H's in a enthalpy diagram to kind of determine what the overall delta H of solution is, or the net. In this case, we're talking about a net exothermic process of a solute dissolving in a solvent. The enthalpy change of the overall process depends on the delta H for each of these steps. So why do exothermic processes occur? So why would something dissolve if it's going to take energy for it to dissolve? So things do not tend to occur spontaneously, i.e. without outside intervention, unless the energy of the system is lowered. So you have a solvent and a solute, and they have a lower energy, and you get kind of this, I mean, you can kind of see the steps. So this would be an endothermic reaction to make this solution. So you need some type of piece that kind of changes it. So we do know that the process in some processes, like the dissociation of ammonium nitrate in water, heat is absorbed, not released. So this would be like the example of a instant ice pack. So that's what ammonium nitrate is going to do when it comes in contact with water. It gets very cold. So why does it happen spontaneously? Well, enthalpy is only part of the picture when we talk about the making of this solution. The reason is that the increasing disorder or randomness or entropy, which is what we'll call delta S when we get to it, so the entropy or the randomness of a system tends to lower the energy of the system. So when you have two separate things and then they combine, entropy increases. You have greater randomness going on. So even though enthalpy may increase, so it's an endothermic reaction when we talk about heat of the system, the overall energy of the system can still decrease if the system becomes more disordered. Things become more, kind of random and mixed up. Now, another aspect when you think about solutions, so let's say I have some nickel. That's that image there on the left. And I put some nickel in hydrochloric acid. So the nickel's those metal ball bearings, and I put it in concentrated hydrochloric acid. It is going to combine, and you end up getting this green solution. Now, just because the nickel disappears, so you're not going to see it anymore, you're going to end up getting a solution, this green solution. So you have clear hydrochloric acid, nickel metal, mix it together, now you have this green solution. So did it dissolve, did it not dissolve? Well, in reality, this one didn't dissolve. Okay, this would have been an actual chemical reaction where you changed the substances. So it needs to be clear that not just because things disappear, it doesn't always mean that it just dissolved. It didn't necessarily dissolve. It may have reacted instead. So need to be careful in that case. So dissolution is a physical change. So something dissolving is a physical change. You can get back the original solute by evaporating the solvent. So in this case, I have the nickel. I put it in the hydrochloric acid. I get the green solution. If I evaporate off all the water, I do not, this last image on the right, I don't get my nickel metal back. I don't get my ball bearings back. I end up with this green solid. So that indicates that a chemical reaction occurred because I was not able to get back my starting material. So if you can't, the substance didn't dissolve, it reacted. So when you take table salt and you dissolve it in water, okay, that is dissolving because if I evaporate off the water, table salt comes back. It's identical to what I put in. So that's just something you need to be careful of when considering this. All right, so that's where we're going to leave it for today, and I will see you on Thursday.